So the important thing is that it is to be understood that electromagnetic oscillations are homomorphic to the oscillation of a pendulum. That is, if I have a cavity, for instance, a parallel plate cavity, and if I study the electromagnetic oscillation inside this cavity, then it might be something like, if I were to write it using the notation of my lecture notes, I can write down the solution of this cavity quite easily, which is something that you have done before. Then the cavity would have something like E0t sine KL Z, for instance. It will have a solution something like this. And then that would be a cavity mode. And if you look at the cavity mode, then you will find that the E0t is something that is time harmonic, and it will be given by E0 cosine of omega t plus psi, for instance. In other words, if you look at electromagnetic oscillation between two parallel plates of PEC, the oscillation is time harmonic. And what it means is that this oscillation is very similar to the oscillation of a pendulum. Okay, so if we have a pendulum, for instance, if I have a pendulum and then it has a mass m, and then it was attached to a wall with a spring, and let's assume that the displacement of this pendulum from the mean is x. Okay, then if you were to look at this pendulum, it's going to oscillate back and forth in a sinusoidal fashion. And if you look at the oscillation in the electromagnetic field cavity, the oscillation has the same behavior. It's going to be time harmonic. And we are going to use this time harmonic nature of both kinds of oscillations to understand the quantum theory of light. Okay, so before we do that, then we would like to understand the quantum theory of a pendulum. So what I'm saying is that if you have something like this, you're going to have electromagnetic oscillations between this, and the fundamental mode might be something like this, and then there's the next higher order mode, which is something like this, and then there's next higher order modes. But each of the modes will have a resonant frequency, but if you were to observe that mode, it actually is going back and forth and up and down, just like a mechanical pendulum. So instead of studying the quantum theory of light directly, we study the quantum theory of a pendulum to begin with. Okay, so what I'm saying is that if you have electromagnetic fields, it has many, many oscillations, many, many modes. Each of the mode is homomorphic or analogous to a pendulum. Okay, so if you can understand the quantum theory of a pendulum, then we can understand the quantum theory of light. And I like to say that you can think of electromagnetic theory as being due to a coupling of simple harmonic oscillator. Say if in one dimension, you can think of a string of weights coupled to each other by spring constant. And if you were to set this in motion, you can actually send a wave down this coupled harmonic oscillator, which is a series of weights coupled to each other by springs. And the electrical engineering equivalence of this would be a LC tank circuit. So if I have just one LC tank circuit, it will have one resonant frequency, but if I couple both of them together, it will have two resonant frequencies. And then if I couple 3 or 4 of them together, I have more and more resonant modes. You can solve the equations from electrical engineering quite readily. And then in the limit, when these oscillators are infinitely many and becomes a continuum, you have the transmission line model. We actually derived for you to show that the transmission line model can be derived from the lumped element model, and eventually it will have infinitely many modes. Hence, you can think of this can be generalized to 2 dimensions, and 2 dimensions describe the propagation of waves in 2D space. And then you can extrapolate this to 3 dimensions, which is what Maxwell's equations are. You can think of Maxwell's equations is a way to represent the propagation of coupled harmonic oscillators in a 3D space.